Hello, I'm the mischievous Mr. Daycock, and today I'm going to be teaching you how to solve the most basic forms of recurrence relations. So here we have a recurrence relation. It tells us that un plus 1 is equal to un plus 4 with, and remembering this is always very important, an initial condition of u0 equals 7. So what I'm going to do is I'm going to write out some parts of this recurrence relation. So we know that the first term, or arguably the 0th term, u0, is 7. We can also know that the rule for this, the recurrence relation rule here, is un plus 4. So to get to the next term, un plus 1 is equal to un plus 4. So what I have to do to get to u1 is add 4. So I'm going to add 4 and get 11. And then u2, to get to u2, well, what do I have to do? Well, I have to add 4. That's what it's telling me. So I get 15. Now, let's get to the next one. u3, well, I have to add 4, so I get 19. And now, this carries on, of course. What are we going to deal with? How do we think about this in terms of nth term? Because it's asking us to solve it, and solving an equation like this means that we are looking for its closed form. We're looking for a form of just un equals something in terms of n, rather than in terms of previous terms. Well, what I'm going to do is I'm going to say what's happening from the start. So from 7 to 11, I'm adding 4. From 7 to 15, I'm adding 2 lots of 4 to get to that point. From 7 until 19, I'm adding 3 lots of 4. And this tells us that what's really going on here is a set of multiplications. We're starting out with an initial point 7, and to get to whatever term we're at, notice here the 3 here is the same as the 3 here. The 2 here is the same as 2 here. We're taking 7 plus n times 4. So our un is going to be equal to this. 7 plus n times 4. Now normally we wouldn't write it that way. Normally we would write it as 4n plus 7. And this here is our solution to this recurrence relation. This is the closed form, un equal to 4n plus 7 is our closed form of the recurrence relation given at the top. This is it solved. And why is this valuable? This is valuable because at this point we can just plug in any value of n and get out that point in the sequence. I don't have to work my way through the sequence like I would with the recurrence relation. Here I can just put in the value of n. So I could say n equals 100, and rather than having to do 100 additions of 4, I just plug it in, and I get u100 is equal to 400 plus 7, which equals 407. Brilliant. And now what's important to note is that any recurrence relation where the rule is adding, so we've got un plus 1 is equal to un plus something, we'll call it a, is always going to be of the form, in fact let's not call it a, let's call it c, is going to be of the form, solves to the form un is equal to some an, not subscript there, an plus b. Okay, and that's really, really important because we're going to use that form for the next question. Let's solve the recurrence relation un plus 1 is equal to un minus 6 with un equal to 11. So as before, let's look at the sequence. Our u1 is 11. Our u2, well, what are we doing? Well, we're subtracting 6 each time, so that's going to give us 5. Our u3, that is going to be negative 1. And our u4 is going to be -7. Now notice a slight difference here. This one started with u1 equal to 11, not u0. So that gives us a slightly different situation. Now we know our solution is going to be of the form un is equal to some an plus b. And we also know what this a is, because what's happening each time? Well, it's going down in 6. So the thing we're multiplying by, how many lots here we subtracted 6. Here we subtracted 2 lots of 6. And here we subtracted 3 lots of 6. So what are we getting? Well, the a must be our -6 because we're getting 2 lots of -6. For the next one, for u4 would have 3 lots of -6. So we can say that un is equal to -6n plus b. Now at this point you're probably quite tempted to say, and I know what b is 11, but it's not quite right because this says u1 equals 11. So what we're going to do at this point is we're going to take n equal to 1 and see what we get. Then we get u1 is equal to -6, because -6 times 1 is -6, plus this b term, which we're not sure what it is yet. But we do know what u1 is. u1 is 11. So I get 11 is equal to -6 plus b. And that tells me that b is equal to 17. Therefore, my solution to this recurrence relation, un equal to -6n plus 17, not plus 11 in this case. Or you could, of course, write it perhaps slightly neater as 17 minus 6n. And that is our solution to this recurrence relation. Now, that's an example when we're adding. Let's look at an example when we are multiplying. So solve the recurrence relation un plus 1 is equal to 5 lots of un with u0 equal to 2. So as before, I'm going to write out some terms. I get u0 is 2. I get u1, well, what do I have to do? I have to multiply by 5, so that must be 10. I get u2, well, that must be 50, because what I'm doing each time is multiplying by 5. And u3, well, 50 times 5, that's 250. And this is what I'm doing each time. I'm multiplying by 5. So again, what's my recurrence relation going to look? What's my closed form going to look like? Well, here I multiplied by 5. Here I multiplied by 5 twice, which is the same as multiplying by 25. Or, to put it another way, 5 squared. Here, to get to this, I multiplied by 5 3 times, or 5 cubed. So in this case, notice that the n is our power, because what we're doing is doing lots and lots of multiplication. So, to consider that, what we're going to do is we know that it must be something like un is equal to 5 to the power of n. And at this point, it's tempting to go, and we need to add something, because obviously with u0 equal to 2, we need to add something to get it right. But actually, what we have to do in this case is, because it's all about multiplication, that extra constant needs to be multiplied. So we've got dealing with some un is equal to b multiplied by 5 to the n. And to find out what that is, well, I'm going to put n equals 0, because the term we've been given, the initial condition we've been given, is that u0 is 2. So I'm going to put u equal to 0, plug that in, and I get u0 is equal to b times by 5 to the power of 0, or u0 is equal to b, because 5 to the 0 is 1, and therefore u0 is 2, so b must be 2. And that gives us our closed form of this recurrence relation, which is that un is equal to 2 lots of 5 to the power of n. And we use the brackets to indicate that 2 is our coefficient and not part of the thing that's being raised to the power. And this here, this is not correct because we don't have that multiplication. We don't have that factor here that allows us to get the correct initial condition. And just like the one before, we have a general form where un is going to be equal to b times by a to the n. And notice the analogous relationship here between a and b, and the a and the b in our general form over here. A times n plus b. Here we've got a to the n, a to the n times b. Okay, and let's use that form to solve our very last problem we've got here. We've got solve the recurrence relation. Un plus 1 is equal to negative 2 lots of un. U1 is equal to 7. So we're going to use our form that we just established. Un is equal to b times by a to the n. But we have a nice little bit of information, because what are we multiplying by repeatedly? We're multiplying by this negative 2 repeatedly. So the a, the thing that's being raised to the power of n, must be negative 2. And so I get un is equal to b times by negative 2 to the n. Oh, need to use some extra brackets here to ensure that our negative is in the right place. So negative 2 to the power of n, and actually quite nicely, due to bid mass, we don't need to put another pair of brackets on. And now we want to work out what this value of b is. Well, we're just going to plug in our value of n. We've got n equals 1. Plugging that in, we get u1 is equal to b times by negative 2 to the power of 1. Negative 2 to the power of 1 is negative 2. So that tells us that u1 is equal to negative 2b. And therefore, and we know that u1 is 7. So we get 7 is equal to negative 2b. And that tells us that b must be equal to 7 over negative 2. Or, slightly simpler, b equals negative 7/2. And then therefore we get our final form of the recurrence relation. Un is equal to negative 7 over 2 multiplied by negative 2 to the power of n. And that there is our general, our solution, our closed form to the initial recurrence relation. Un plus 1 is equal to negative 2 un with u1 equal to 0. And just like before, we could find out what u to the power of 100 is. Oh, sorry, what u100 is, and that would be just negative 7 over 2 multiplied by negative 2 to the power of 100, which is a very large number. So I'm not going to write that down for you. Okay, thank you for watching. Hopefully you learned something from this, and I'll see you in the next video where we go for slightly more complicated versions of these recurrence relations. Thank you very much. Goodbye.